Okay. Okay. So next, we are going to hear from Jaeyoung Jung, who is a postdoctoral scholar working with LEAP. Jaeyoung has his PhD in civil and environmental engineering from Seoul National University in South Korea. His research areas include multiscale mechanics, theoretical and numerical analysis of flow physics, and canopy flows, and machine learning. Thank you so much.
Thank you for interesting me. Hello, everyone. Thank you. First of all, thank you for your time joining my presentations regarding research update. And today I would like to introduce my work, which is multiscaling framework for a macroscopic modeling of airflow-canopy interactions. So our interest is airflow-canopy interaction problems, and there is a multiple process between airflow, atmosphere, and canopies. First of all, like there is biophysical and chemical processes such as gas exchanges and radiation, heat, and humidity fluxes. And another essential component is wind dynamics regarding turbulence flow in or around the canopies, and which plays a key role in the various processes between the atmosphere and canopies. And so in order to achieve like a better understanding of a microclimate, the accurate predictions of airflow in canopy is quite important issues. So this study mainly focused on providing a more advanced model for canopy flows. But first of all, I want to start briefly recap the existing work on the biophysical and chemical process first, and which includes the heat, humidity, gas fluxes exchanges, and which is related with photosynthetics and greening and sunlit shade and phenology and so on. In order to analyze the complex and multiple processes, there are a bunch of options. And one of the most widely used and cheapest and simplest one is a single layer models. This model regard the canopy layer as a big leaves, relying on the homogeneous and isotropic canopy assumptions. And I want to point out this model requires at least 1 point wind speed to assess aerodynamic conductance regarding turbulence fluxes between atmosphere and canopy layers. And more recently, multi-layer model was proposed. This model can reflect the vertical heterogeneous structure of the canopies, but still rely on the horizontally homogeneous and isotropic canopy distributions. And this model requires 1D canopy wind profile for estimate the turbulence fluxes between each layers. And as the computational powers keep growing up, the demand for the more accurate prediction also increased. So what's next? In my opinion, it would be like much more advanced and accurate model that can handle heterogeneous canopies, and so that we can deepen our understanding regarding the microclimate situations. So these kinds of like a more complex model might require 3D wind velocity fields, but this is quite challenging stuff to provide high fidelity simulations in these scales, in this microclimate scales, due to its complexity and the multi-scale nature of it. So aerodynamics in canopies mainly, basically it regards complex fluid structure interaction problems. And this occurs on a broad continuum of scales, start from leaf scales and trees and bunch of trees, forest and global scales. So if we want to provide high fidelity simulations, then the best choice is the direct numerical simulations on the fine resolving meshes, which resolve every single scales, all the scales in the canopy and flow structures by imposing a world boundary condition along the solid and fluid interfaces. But this requires a lot of computational cost. So this method can cover a bunch of leaves or branches. So this is not feasible for our scale of interest as microclimate simulations. So this is not feasible way for our goal. Another existing approach is canopy drag models. And this model neglect the physical presence of the canopies and just add this kinds of additional source term here, and which has a meaning of physical subgrid scale canopy drag effect. But this method is really easy to implement, but this method adopt homogeneous canopy assumptions. So this method also can be applicable for quite large scale where the homogeneous canopy assumptions make sense. If we apply this method on like heterogeneous canopies, then it can be problematic because in these cases, the source term FD will contain the resolvable information of like some part of inertial effect due to the heterogeneities. So the parameter estimation for drag coefficient CD will be problematic in these cases. Another way is adopting a 1D analytic models. This model adopt like additional assumptions, which is neutral or steady state assumptions. For the flow over the canopies, the 1D model is used as world models based on the concept of roughness height. And for the airflow inside the canopies, we solve this reduced version of momentum equations. This can be derived by applying a neutral state assumption and neglecting the inertial part. Then we have this. And also utilizing a gradient models and a mixing length hypothesis. And we also use canopy drag model, then we can derive the 1D profile inside of the canopies. And those models also adopt isotropic and homogeneous canopy assumptions, so it cannot applicable smaller scale problems where the anisotropy or heterogeneous canopies cannot be negligible. So the existing method can be applicable only for a quite large scale where the homogeneous assumptions make sense. So due to this assumption, those two methods have some limitation in terms of downscalings. And for the DNS, a fully resolving strategy has also its own limitation in terms of upscaling due to the computational cost. So there is a missing gap from here to here. And the present study aimed to bridging this gap by multiscaling method. So in this range of scales, our scale of interest might be a kilometers or hundreds of meter scales for the entire computational domain. In this case, the grid size might be a few meter scale, at least 50 centimeter scales. Is much larger than leaf or smallest structure of the canopy. So we should consider a coarse grid model, which is the model where the grid size is larger than smallest structure of the solid part. So we need to formulate coarse grid model, and it should be capable of heterogeneous situation, and it should be implemented so that it can cover the wide range of length scales to bridging the missing gap. So for this purpose, we upscale the problems based on the volume averaging theorems. In this, if we upscaling, if we taking the volume averaging, then the solid part and fluid part in the given cells homogenized as follow, and they're represented by porosity defined by volumetric ratio between fluid and cells. Then the heterogeneous canopy fields can be represented by heterogeneous porosity fields. Likewise, upscaling the incompressible Navier-Stokes equation, which is not feasible in our scales, then we have volume average Navier-Stokes equation, which might be feasible. And this formulation has two different scales. One is the resolvable scale, and the other is subgrid or unresolvable scales. For the resolvable scale, can be directly solved the numerical approximations on the finite grid system, but the subgrid scale terms cannot, because it includes specially fluctuating component, which is microscopic informations, much smaller than the grid size scales. So it should be replaced with the surrogate models, and the surrogate model should be a function of resolvable variables to close the problem to make this problem solvable. In order to do that, we proposed the following multi-scaling framework, which consists of a training step for microscopic problem and simulation step for macroscopic simulations. For the training steps, we will consider a unicell problem, which is a representative and periodized microscopic structure of the canopies. And we will idealize it to produce tons of unicell problem with varying parameters. Then for each unicell problem, we can directly compute resolvable variable by taking cell averaging over the entire unicell domain. And we also directly compute subgrid scale terms. Now we need to find out functional relationship from left to right, and which will be done with supervised machine learnings, and it will be coupled with volume average Navier-Stokes equation solvers. Then in the simulation steps, we will gonna solve these equations, and here the subgrid scale part will be replaced with the ML-based surrogate model. Then the problem is closed, we can solve it, then we can perform the macroscopic simulation for the canopy flows like this. So in order to accomplish this framework, we need to complete two tasks. Firstly, we need to implement a stable and accurate numerical scheme for resolvable part of the volume average Navier-Stokes equations. And second task is we need to train the ML-based surrogate modeling for the subgrid scale terms in volume average Navier-Stokes equations. For the first task, we developed a novel numerical schemes, and the story is quite long. So to make this short, like we implemented a high order method based on these three schemes. Firstly, for temporal integration, we use a third order Runge-Kutta method, and for the first derivative, special derivative of the flux term, we implement odd order a finite volume Wiener method, and the second order derivative we use even order Wiener method. And we also formulate our scheme so that it has well-balanced property to achieve advanced force balance between flux and source terms. Here, the blue color terms represent the net pressure force from ambient fluid, and this red term represent the pressure force from solid to fluid. So in order to achieve balance, perfect balance between two terms, it should be treated very carefully. And this example shows like stationary conditions with zero velocity over the irregular porosity. And our servers preserve the stationary exact solution up to round operators. If the scheme don't have a well-balanced property, then the unwanted flux comes occurs at the level of truncation errors, and it will contaminate the entire domain. But fortunately, our scheme has well-balanced property, so it's good. And we also consider Riemann server, which can treat strong heterogeneity situations, including discontinuous porosity. So in order to achieve this Riemann server, we firstly we derive the exact solutions of this discontinuous problem over the discontinuous porosity, and then we provide and prove some mathematical theorems regarding uniqueness and existence theorem of the solutions, discontinuous solution over the discontinuous porosity, and we confirm that our Riemann solvers based on the theorems designed like to be satisfied the theorem. So our Riemann solvers can capture all the types of discontinuous solution over the discontinuous porosity. So, and this study is prepared as a draft entitled to like this. For the task 2, we need to build the ML-based surrogate models. First of all, in order to verify that our framework works or not, here we consider very simple unit-cell problems with only one single scared cubes. And varying the size of cubes and the Reynolds number and the flow angle, we produce tons of simulations and then train it and coupled it with the volume average Navier-Stokes equations. Then in the solutions simulations tab, it gives this kinds of a close resolution simulation, and which shows good agreement with the reference solutions, DNS solutions. So this is also another type of work. My takeaway from here is if the unit cell problem is well designed, then the multiscale framework can yield accurate prediction. So now, at this moment, we are challenging for the realistic canopy flows. And the major key questions we are facing now is how do we design the unit cell problems for the plant canopies? So in order to do it, we implemented the artificial tree generator comprised of a fractal branching part and a leaf structure approximating part. Then we have this kinds of synthetic tree. If we recognize the dominant species of the tree in the target area, then we can generate this kinds of synthetic tree by giving those information to the artificial tree generator. If we divided the tree into two parts, the part 1 is crown part and part 2 is trunk part. Let me explain about part 1 first. And we also implemented sampling modules. Using this module, we can sample like this, the smallest structure inside of the canopies. And actually, this is what have we done so far. And after here is kind of a plan, future plans. So if we sample here, then we can extract some geometrical parameters such as porosity and canopy area index comprised of leaf area index plus branch area index. And we also extract a mean space between leaves or branches. And a lot of number of sampling gives a PDF function for each parameters. And then based on this PDF function, we will generate like statistically ideal and representative unit cell geometry. This was for the part 1, and part 2 is much simpler because it's only contain like trunk part. So But the unit, basically, we will reserve it using a boundary condition if it's possible. But if not, when the grid size is much larger than diameter of the trunk, then we should consider unicell problem. The size of unicell problem can be different depending on the flow condition or like, so yeah.
Maybe one or 2 minutes left.
Okay, I got it. So yeah, so it's like for the laminar flow, the become heat this side, and for the turbulent flow, the unit cell should be much larger. And this is our idea for the how we design the unit cell problems. And using this geometry, so we're gonna train the surrogate models, and eventually, we believe that our method can be extended to can cover a wide range of scales by extending it to multiple steps recursively. And this is a summary. And thank you so much.
Thank you so much, Jaeyoung. We are over time, but hopefully people can stay for a couple of questions. Does anybody want to start with a question?
Thank you for your talk. You already implement the single cell model online, right? Like the simple, the unit cell model.
Yeah.
Like you train the neural network and you put it in the numerical solver and run the online simulations.
Yeah, we have a procedure, but we have a pardon?
I mean, you have finished like training your neural network and you put it couple it into the numerical solver. And right. And you perform some simulations, right?
Yeah. It's
And
for the verification stage,
Yeah.
we do it with a very idealized geometry. And then now we are trying to move up to the next phase with a more realistic geometry. So
did you face some numerical instability when you run the online
actually it's not, because our server is discontinuous server. So even though there is a big difference between each cells, it can capture some discontinuous solution due to that thing. So it gives some solutions, even though, we need to check it is, physically reasonable or not. But so far we don't have instability issue yet. So
Thank you.
thank you so much.
Hi, what real world application would this apply to? Like, for example, modeling wildfire spread or potential spread?
Okay. It's you mean the application area of model.
What would this be used for out in the world? For example, I could see that wind moving through a forest would impact wildfires. That's just an example. Like if you're trying to predict where the wildfire could go and how fast it could spread.
In my opinion, our server is can provide very high resolution simulation for aerodynamical sense. So before this method, actually, is the previous studies cannot capture the how to say the effect, the mechanical interaction between the canopy structure and wind. So it should be assumed, and with very powerful simplifications, and which hinder the accurate prediction for short-term time. So it's, in my opinion, it's our method can offer more accurate simulation in terms of which wind behaviors interact with some solid structures. How to say, and we already checked that our schemes can cover a wide range of like scales. So if we scaling down, it converges it to DNS, and it scaling up, it converges it to direct first model. So it can bridging the missing gap. So it can include like existing method application, but also it can offer some area the existing scheme does not reserve it. Like, is it correct for your?
Oh, I'm just wondering what this is used for. It's okay.
Oh, okay. It's like,
What's the time frame? What's the interval? 24 hours or a week or?
yeah, if you want to like apply our method to large scales, then the temporal scale also become larger. If you want to like apply our method to very short-term scale, then we can reserve the short-term scale phenomenon too, because it has very wider range of coverages in terms of scales, I guess.
Thanks for this nice talk, very informing. I wonder if, like, when you see someone doing climate modeling, they usually say, oh, we improved the parameterization and now this model is outperforming all the rest. Or they're using a new formulation and say, oh, no, this new formulation is now outperforming all the rest. So, but then there's also a lot of uncertainty in different aspects. But I wonder, in your approach, what would be, or if you have any benchmarks to say or showcase that really this is an improvement compared to what has been done before?
Actually, that one is our next step to provide a realistic validations. It's like at this moment, the advantage of our like we checked our advantage of our models in terms of mathematical aspect so far. It mathematically more stable and mathematically can cover a wide range of scales. So, and yeah, your question might be our next pace. So we are looking for a very nice site observation data so that we can show our superiority compared to existing ones. The existing method cannot capture, but our one is captured. Like, yeah, it's like, yeah, we are trying to find the good application areas like that. So, but not yet. I cannot say, yeah, always this my model is always good in the physical application. Yeah, because I don't have any evidence. So yeah, let's yeah. Thank you.
And we have a question from the chat. Sorry if I put the inflection in any weird places in these words. I am not a modeler. Shouldn't it matter that the trunks are currently spaced in a diamond grid? There are genetic algorithms for plotting. Is this what you're talking about now? Like, I don't think it would be as laminar.
Okay, it's a kind of like simple schematics. It's kind of like it's kind of a simple schematics examples to show you depending on the flow and the geometrical structures, the unicell can be changed. So this arrangement is kind of just examples, and for the realistic cases, we will observe with like remote sensing. We can have like some more exact configuration of it, though. And here is like, yeah, it for the if I compare between the laminar and turbulence, actually there were some studies is related with the question whether the macroscopic turbulence can survive inside of this porous media. It depends on the porosity and it depends on the pore scale length scale of pore size and the flow speed. When the porosity is quite high, then the macroscopic turbulence cannot be survived inside of this domain. So in that case, we can use the unicell problem with this blue line. But if there is some macroscopic structure larger than full scale, then we should consider larger size of the unicell problems. So in order to address these issues, it's kind of just the example figures.
Do you have a term for the distribution of the leaves inside your cell? Because with wind, they vary. You have a Do you have a term in your equation?
No, I'm sorry, we're at 1:15. We do need to respect everyone's time. I'm sorry. So thank you, Jaeyoung.
Thank you so much.
Thank you so much.
Thank you so much.
Thanks everybody. And again, sorry for going a bit over time, but there is pizza and some salads in the back, and we hope you'll stay for some lunch. Thanks again, Jaeyoung.
Thank you so much.